Hello and welcome back. In this lecture, we're going to discuss about the Mish activation function. But before we do that, we're gonna need to have a look at the soft plus activation function because the Mish function basically depends on the soft plus. So the soft plus activation is basically log 1 plus e to the power of your input. X here is your input. Now, of course, we can scale it. So we can scale this whole function by 1 over beta. And we can also scale this x by beta. So beta is a hyperparameter you can set. If you set it to 1, then you just end up with a log 1 plus e to the power of x. So this is the soft plus plot, and basically if you want to compare it to Relu, you can have a look here. So the red plot is Relu and the blue plot is soft plus. Now realize that for small negative values, from basically from negative to up until 0, then the output is positive. It's still positive, okay? And here we don't really want that. Now here you only have 0 once you cross negative 3, but all the values that are bigger than negative 3 are going to be basically a positive value according to the soft plus function. Okay, so now let's have a look at the Mish function, which depends on the soft plus. So the Mish function is basically a modified gated form of the soft plus activation function. This is the soft plus activation function we saw, which is logarithm of 1 plus e to the power of x. Now here, what we do in Mish, we first run it through a tanh activation function and then multiply this with the input x. So it's somehow similar to the swish activation function. It's basically the input is multiplied by something. Here in swish, we're going to multiply it by the sigmoid of the input. And in Mish, we're going to multiply it by the tanh of the soft plus function. And when we do that, then for small negative values, we don't have a positive value anymore, as we saw in soft plus. So for small negative values from negative 3 to 0, we don't have a positive value anymore. So from negative 3 to 0, we have a negative value, as you can see here. And again, it shares the same thing as Relu when your values become more negative. So once you cross -4, then basically it becomes 0. So these are some advantages of the Mish. Number 1, it's unbounded above, so there's no saturation. Number 2, small negative values are not 0. So the small negative values here are not 0, but they're a value very close to 0. And this basically allows a better gradient flow rather than having a hard 0 bound as in Relu. For all negative values, if your output is 0, such as Relu, then you might have some problems in optimization and in gradient flow. And finally, the third advantage is that it's continuous. So it's a continuous function, unlike Relu, which is basically discontinuous at 0. Whenever you have 0, you have whenever you have a negative value, you have 0, and whenever you have a positive value, it stays positive. So it's discontinuous. Relu is discontinuous, but the Mish activation function is continuous. And of course, when you have a continuous activation function, then this will be very effective in optimization and generalization as well. So this is the Mish activation function compared to other activation functions. We learned about Mish, tanh Relu, sigmoid, leaky Relu, soft plus, and swish. These are the activation functions we learned about. Here, this figure compares all of them together in one plot. And finally, let's have a look at the results of the Mish activation function. And as you can see, when it's applied to SqueezeNet, which is a CNN architecture, then it's going to have an increase in the top 1 accuracy by 2.15% from Relu. Okay, so the Relu activation function achieves 60.92% top 1 accuracy. The swish activation function that we talked about before Mish achieves 62.1%, and finally the Mish activation function achieves 63.07%, which is basically 2.15% increase from Relu. So this is for SqueezeNet, and basically it outperforms Relu in all the CNN architectures mentioned here. It outperforms Relu. But sometimes for some CNN architectures, then the swish activation function still performs better, such as DenseNet with 169 layers, so DenseNet 169, and you have WRN here. So in these two architectures, in which the authors compared, basically swish activation function performs better than Mish. But in any case, all of them perform better than the relu activation function. So these are the results of the Mish activation function, and the Mish activation function has been applied recently in YOLO version 4. We're going to learn about YOLO later on, which is basically an object detection framework. And for version 4, they've used the Mish activation function and they've achieved better results and faster results. Okay, so that's it. Thank you very much, and I'll see you next time.